C.Wiechers to invite us to this great workshop. Okay, in this talk, I want to introduce what are the main activities of group. Okay, first I want to introduce you the group. The group members are L.Rivera, Lorena, Velázquez, and myself, and Professor José Lucio Martinez, and we have some students that were present here, Carlos Saavedra, and some master students, and some undergraduate students. Okay, I think we have like a quantum quest in the University of Guanajuato. So we want to develop new. We want to enter to the development of quantum technologies, and also study the fundamentals that govern these kind of technologies. And also we want to, if we understand the fundamental, we can optimize how they perform. And since in this field we want to go in the direction to develop quantum cryptography systems, we know that the security in information is one real issue in the world. So we want to, because actually we know the news of the quantum computer. So in the near future, actually in the close future, we will see that most of the conventional encryption system will be break because due to this computer outperform any classical computer. And also we want to prepare human resources in this field. So in order to be prepared for the new technologies. Okay, this is the overview of this talk. It's more or less, is that first I will introduce what is in general, what are the parts of the quantum cryptography system, and this is the field we are working with. We work in the sources, modern simulation optimization of quantum cryptography system, and fire-based, fire-parrot cavities. And actually, we are developing a quantum cryptography system in the university. So we'll show our first results, the first implementation. Okay, in this part is quite a bit more general. So practically, the quantum cryptography distribution system, as in the same like any other quantum cryptography, quantum technologies, there are many fields that they can join in order to develop this field. So actually, we're working in the implementation, so we're applying most of these parts. But there are many people that work in the protocols, many people work in the sources, and to develop quantum channels that they have losses. We're also working in detectors, actually in the techniques to understand the noise of these detectors, optical fiber cavities, because the quantum memory is one of the possible way to develop a quantum memory is in a cavity. And also there are quantum random generators that there are people that work in quantum error correction algorithms and the privacy simplification, and also we're working in the modeling and simulation of the system in order to optimize the operation of the quantum key distribution. I mark with this blue mark more or less the field we're developing in the university. And later on in the talk, I will talk a bit more about these fields. So first, in the group we develop engineering of states. So in this case, engineering expected correlation in forward mixing. So one of the goals is, for example, we will have a photonic crystal fiber we fill with high thermal optical coefficient liquids. So if we have this liquid in the core, so we can easily modify this output state. So we can engineer the state by modifying the temperature of the optical fiber. So actually, this work will be presented in the poster, the Lorena Velázquez poster, is the number 20. And one of the advantages of this is because in this kind of material, the fiber, we have many degrees of freedom, so we try to exploit one of them is the temperature. And when we reconstruct, reconstruct the phase matching curves of this fiber using different temperatures, we can modify the final correlations. So here the correlation we can express in terms of the joint spectral intensity, and sometimes just by modifying the length in this case or temperature, we can go to the negative correlations to positive correlations, and we also can create the factorization states. So it's one of the tasks in this field. One other sources we can exploit is use the spontaneous parametric dot conversion. So in this case we have a variable rate crystal, and we pump with a Gauss mode, and actually the structure of the mode is directly passed through one of the state, maybe one of the signal or one of the idler. So we work either using developing the model, try to get a more exact model, and also want to implement it in the laboratory or use a collaboration to work in this field. Because one of the advantages of these sources is because we can use the more high dimensional quantum distribution system using this kind of systems. Because in this case we use this pump. The pump mode is the state have the heritage of the structure of the pump, but usually since we have a orbital momentum conservation, if we measure the idler in the mode like a Gauss 00, we get exactly a copy of the state of the pump mode. But this is only one case, because usually we have all the possible combination of states, idler, and signal that keep this rule. Because if we sum the angular momentum of the signal and the angular momentum of the idler, we recover the angular momentum of the pump. So we have all the families of this combination of states that we can exploit for later on for prepare high order quantum cryptography systems. Okay, I want to introduce the scenario. Most of the people are really familiar to the quantum cryptography system. In this case, we have two parties. One is usually called Alice and Bob, and they want to communicate, generating a secret key that they can use to encrypt the message. And one of the advantages is this kind of cryptography system cannot be broken by a quantum computer because due to the nature of the quantum state. But usually, if there is the communication is taking place in two parts. One is the one unidirectional quantum channel. This is for the prepare and measure protocols. And we have a bidirectional communication between Alice and Bob when they perform all the quantum error correction, all the privacy amplification, and the shifting of the keys. But one advantage is if there is in this kind of system, if we have a eavesdropper that can take advantage of the key using one strategy or one hacking strategy. So even that, Alice above can she will leave a signature in the key, so inducing more errors in the key. So then, when Alice and Bob perform the error correction and get the secret key, they can compare the error correction with a limit and get and decide if the channel is secure or insecure. And actually, there's many things that Alice and Bob need to do in order to because it easily can perform many strategies like a blinded detector, that is the most successful technique, but using the proper security when they block all the possible attacks, the system will operate in the normal quantum way, but in this case we have some tasks we need to do. One of these is get the optimization of the final security rate. The final security rate, they have many. There's a multivariant optimization because we have the error correct, the quantum bit error rate. We have the rate of the key. We have the rate for the single photo signal and the error for single photo signal. But in order to estimate all these parameters, it depends on the detector. So in the detector we have many parameters. We have the dark counts, we have the after pulsing, we have the efficiency, we have the dead time. So many of these parameters need to take into account to optimize the quantum cryptography system. We have also the quantum channel. We have the optics that are the internal optics of the Bob and Alice systems. We have the sources, and we have the state preparation that usually we need to use a true random number generator, and we have we need to prepare in the right phase, in the right modulations the system, because taking advantage of all these components, we can optimize this final secret key, and we get the maximum rate we can get in the system. Usually, here we compare 4 protocols. Is the BB84 protocol, the SAR 04, and some decoy states for the same protocol, BB84 and SAR. Usually, this is the final rate compared with the distance. The first two results are, by example, for the standard BB84 and SAR 84. Here, we choose the 3 most important parameters for the optimization. One is the dead time, the frequency, and the mean photon of the signal. Then we have more parameters, but usually they are less important in the optimization. But we see usually in the standard protocols, we only consider the dead time to optimize. We see the optimal is the blue curves, and using a single only one value of dead time, we observe that the rates are decreased. And for example, for the decoy state, the difference is we use 3 states with different mean photon numbers. One of them use one of the mean photon, one of the states is used for the signal, and 2 other states are used for the decoy, in order to reduce the possible attacks of the eavesdropper. So we see that in these cases we have more on a higher distance, but these protocols are more susceptible to choosing the optimization of the dead time. If we don't optimize the dead time properly, we observe clearly that the system becomes less efficient. And this is another part of the talk. This is Faber-Perot optical cavity that we are working with. This cavity is prepared in a bulk system. Practically, it's in a bulk system. They have higher stability, as we can see in the parameters. The refrigerance is less than 1 line width. They show high thickness of 180,000. High coupling. Transmitter is quite low, but still is enough to prepare state. We have the very small tuning capacity, and the size is less than 1 millimeter. And this is really important in order to create a very stable cavities. And this cavity is generated just with a laser carrying a small parabolic surface in this fiber, in the fiber, and this fiber are stick together. And there are some applications we can use. They create the cavity optical filter that usually in quantum system we need a specialized optical filter in order to avoid any possible attack with different wavelengths. And we have some sensors we can use with this cavity. More information, you can see more information in the Carlos Saavedra poster, it's in number 7. And I want to use our lab implementation of the quantum cryptography system. Usually, it's a very simple. It's a prepared measurement. We have a laser. We need to optimize the polarization because all the internal optics of the modules we use polarized antenna fibers. We have intensity modulator and phase modulator and variable optical attenuator in order to prepare the states. And with these two components, we can prepare. You can use the BB84 protocols, the SAR protocols, and the code version. Just choosing randomly the intensity, the mean photon number using the intensity modulator. And since we send information through the optical fiber, we need to encode the information in phases. So we use the combination of phases of 0, half p, pi, and 3 half pi. And depending on combination, we have a random detection when with both we choose another phase is half p. In the combination phases, we have a deterministic detection in both detectors and probabilistic detection when the difference of phases is a semi-integral of p. And this is the schematic part, and we have these models in the lab. And this is the detectors. So we went to in the practice we have almost complete all this system. So we only need to finish the automatization of the system in order to have a portable models. So we can, and then we can use in a real life application. So yes, fine. So this is part of the implementation we are developing in the institute, and actually because we have almost all the components to have a real application. So as we we apply some techniques of quantum error correction, like the cascade. In this case, we compare blocks and compare parities of the also part of the key of Bob and Alice, and we can perform the full error correction with this protocol. Okay. In summary, well, we are engineering quantum state sources using exponential parametric conversion and forward mixing. We are working also in the optimization of QKD protocol using more general models, and actually we have also developed a quantum cryptography system that, because in the practice we want to have a system that we can use either for some real-life applications, and actually we developed some characterized fiber-based optical cavities. Well, this is more or less the talk. We have collaboration in Cedillo with Alejandro Martinez, in the Cinvestav with Mauricio López, in CDS Jesús González, en Universidad Valencia Miguel Andrés, en Unidad Alfred Uren y Jorge Hirsch, and the University of Bonn, Dr. Michel. And thank you for your attention.
Thank you, Carlos, for your talk. We have time for some questions. If you don't have, I can start. Are you doing your own fiber cavities, or are you getting them from Bonn?
No, we're getting from Bonn. We have a internship. Carlos Saavedra is in an internship with the University of Bonn, and he's working with these cavities.
And do you plan to make them yourself in the future, or not really?
I think we will have still the full equipment to develop them, but we can apply the cavities for any other application. So maybe with the collaboration we want to apply these cavities in different systems, like with a security filter in quantum cryptography, for example.
That quantum key distribution isn't really any good until you can solve the authentication problem. What's your view about this?
Yeah, I think this is a useful problem, because usually the eavesdropper can act like if she was Bob. So it's a real this is a real task to solve, because it's like you want to trust the initial communication if you don't have if you're not really sure what is the other party. No, I don't have. I didn't think about this, how to solve this problem, but I think it's a I don't know. I will try to figure out how to solve it, because it's kind of tough to think. If you're communicating with somebody, try to solve, to really identify that is the real person you want to communicate with. No, I think it's for me, still, I'm not really sure how to solve this problem.
Another question? No? Well, we thank Carlos again.